Hello again. This is Math 2115 coming to you from the College of DuPage, and the title of this lecture is Greatest Common Divisor and Least Common Multiple, the Euclidean Algorithm, and more. As always, please be attentive as you watch this video. The greatest common divisor and least common multiple. The largest integer that divides both of the two integers is called the greatest common divisor of those integers. Here's the definition written formally. So if a and b are integers, not both 0, the greatest common divisor d, such that d divides a and d divides b, is called the greatest common divisor of a and b. The greatest common divisor of a and b is denoted by GCD of a and b. The greatest common divisor of two integers, not both 0, does exist because a set of common divisors of these integers is non-empty and finite, because 1 divides both of them. So one way to find the greatest common divisor of two integers is to find all positive common divisors of both integers and then take the largest divisor. And this is done in a couple of examples, but there's more efficient ways, and we'll talk at least about 2 of them. So you could say, what is the greatest common divisor of 24 and 36? Well, if you look at them, the common divisors are 1, 2, 3, 4, 6, and 12 that are common to the two. Hence, the greatest common divisor is 12. You could also ask, what's the greatest common divisor of 17 and 22? Well, these actually have no positive common divisor other than 17, so the GCD of this is equal to 1. Now, it turns out that's an important kind of case. It happens often. And there's even theorems based on this. So if they have no common positive divisor other than 1, we say that they are relatively prime. Again, as a definition, the integers a and b are relatively prime if their greatest common divisor is 1. So using this new terminology, then the GCD of 17 and 22 is 1, and they are relatively prime. Because we often need to specify that no two integers in a set of integers have common positive divisors greater than 1, there's a broader definition. So we say the integers a1, a2, ... all the way up to an are pairwise relatively prime if the GCD of ai and aj is 1 for all of these different combinations, and that's the way we'd write it. For 1 less than or equal to I less than j, less than or equal to n, and I and j can assume any of the values between 1 and n. I is never equal to j because the greatest common divisor would just be ai, but they're pairwise relatively prime. So here's an example. Determine whether these 3 numbers are pairwise relatively prime. Well, the greatest common divisor of 10 and 17 is 1, of 10 and 21 is 1, and 17 and 21 are 1. Therefore, they are pairwise relatively prime. But if we look at 10, 19, and 24, the GCD of 10 and 24, they're both even, so the GCD is at 2 or more, but that's greater than 1. So the GCD is exactly 2, because this is 2 times 5, and this is 2 times 3 times 4. Or 2 times 3 times 2 squared, I guess, if we prime factored it. So we can see that these are not pairwise relatively prime. Now another, and this is actually what I do in practice for problems that are small enough to solve by hand. So another way is to find the greatest common divisor of two positive integers is to use the prime factorization of the integers. So suppose a is prime factored this way, where you have these exponents are associated with the a, and b is prime factored this way. And you could use a power of 0 if the prime's really not there, so b is prime factored this way, where each exponent is a non-negative integer, and non-negative would include 0, where all the primes occurring in the prime factorization of either a or b has been included in the factorization, with 0 exponents if necessary. I guess I said all that, not as efficiently as they did. Anyway, so the GCD of a and b is given by, you take the minimum value of the exponent for each of the primes, and it's pretty easy to show that that in fact has to be the GCD. So that's a very quick way to do this, and for a small problem, I will tell you this is the way I usually do it. Here's an example. Okay, so we look at 120 and 500. Well, 120 is prime factored as 2 cubed times 3 times 5. 500 is 2 squared times 5 cubed in this prime factorization. So we're looking at the minimum of these. So when we look at 2 cubed or 2 squared, we say, well, it has to be 2 squared. Here we look at 3 to the 1, and this is 3 to the 0, so it's 3 to the 0. And here we have 5 to the 1 and 5 cubed, and so it is 5. So 20 is, in fact, the greatest common divisor. Now, prime factorizations can also be used to find the least common multiple of two integers. Let's define what that means. The least common multiple of positive integers a and b is the smallest positive integer that is divisible by both a and b. It's bigger than them. It's the smallest number that they both go into evenly. The least common multiple of a and b is denoted by LCM of a and b. And it's not hard to prove that the least common multiple of a and b, if a and b have the same prime factorizations that we talked about before, you're going to take the maximum exponent for each of the primes in their common prime factorization, the primes that are there. You take the maximum of the exponents, and that is going to be the least common multiple. Let's apply that technique to example 15. So here we have 2 cubed, 3 to the 5th, and 7 squared. So we got 2 cubed and 2 to the 4th. That means 2 to the 4th is going to be in the LCM. We have 3 to the 5th and 3 cubed. That means that 3 to the 5th is going to be there. And we have 7 squared and 7 to the 0 power. That means 7 squared is there. And I didn't bother to multiply this out, but that is the least common multiple of those two numbers. Now there is a relationship, and we're going to show it, between the greatest common divisor and the least common multiple. And I think it's a little bit surprising, and it can be proven, and actually I've even asked questions about this on tests before. Here's what it is. If a and b are positive integers, then a times b is the greatest common divisor of ab times the least common multiple of ab. You might want to take a shot at proving that. That's actually interesting. But now we're going to move on to a better way to do it than what we talked about. Now, I'm going to tell you that I don't do the Euclidean algorithm whenever I am on a small problem doing it. I do the prime factorization. But this actually is more efficient and easier to code, especially for big problems. So it's called the Euclidean algorithm because it was around even during Euclid's time, and he included a description of this algorithm in his Elements. Okay. Now, before describing it in detail, we're just going to show how to use it. So just follow these steps, but these steps end up actually being the proof as well as how to do it. So we want to find the greatest common divisor of 91 and 287. So first we divide 287, the larger of the two numbers, by the smaller. So we take 91 into 287. So 91 goes 3 times with a remainder of 14. Now, that remainder is not 0, so we're not done yet. And any divisor of 91 and 287 must also be a divisor of 287 minus 91 times 3 equal 14. Okay, so and any divisor of 91 and 14 must also be a divisor of 287 equal 91 times 3 plus 14. Hence, the greatest common divisor of 91 and 287 is the same as the greatest common divisor of 91 and 14. So you see what we're going to do is we're going to do this again, but now we're going to take the quotient and this remainder, and we're going to divide the remainder into the quotient. So we're taking 14 into 91. So that means 91 is equal to, the quotient is 6 this time, with 7 left over. So I take the remainder and I divide it into the quotient. And so when I do that, I have this, and this is what the division algorithm says. It is 91 is equal to 14 times 6 plus 7. Because any common divisor of 91 and 14 also divides 7 because of this, and any divisor of this divides 91, it follows the GCD is the GCD of 7 and 14. So I can do it again. This time I continue dividing 14 by 7, and we get 2. Now notice that the remainder here, it went evenly, so it's 0. That means we're done, and that means we go to the next, so we hit 0 as a remainder. That means end of the algorithm. Then we go back, and the last non-zero remainder is the GCD. And this pretty much says that, just what I just said. Okay, the Euclidean algorithm is based on the following result about greatest common divisors and division algorithm. And we call it a lemma because this is something that we use to prove it. So let A equal BQ plus R, where A, B, Q, and R are integers. Now realize that this means if I divide A by B, I get Q as a quotient with R as a remainder. So if that is the relationship we have, then the greatest common divisor between A and B is the same thing as the greatest common divisor between B and R. And notice how we used that repeatedly before. And you can test that out, and here's a little bit of a proof. So if we can show that the common divisor of A and B are the same as the common divisors of B and R, then we'll have shown what we were supposed to in this lemma. A lemma is a helping theorem because both pairs must have the same greatest common divisor. Okay, suppose that D divides both A and B. That means that this is true, and that equals R. Hence, any divisor of A and B is also a common divisor of B and R. Likewise, suppose that D divides both B and R. Then D also divides BQ plus R equal A. Hence, any common divisor of B and R is also a common divisor of A and B. Consequently, we have proven the theorem. This is the same as that statement. So now what we do is we start with A and B, and we say that A is bigger than B, and say we take the remainder 0, we just call that A, so A is here, but we divide that by the remainder B, and I don't like the notation too much. We divide it by B and take this remainder, and then what you do is you take R1 and you divide it by R2. And you get another R. You keep on going until you hit 0 as a remainder, and the answer is the last non-zero remainder. So eventually a 0 occurs, and because you have that you cannot have more than 8 terms here. So from lemma 1, they all have the same GCD, and so that says that the algorithm works. Let's use the algorithm, which is more the kind of question I might ask you on a test. So what's the greatest common divisor between these two numbers, and using the Euclidean algorithm? Okay, so first thing you do is you divide 414 into 662. That goes one time with 248 as a remainder. Now you take 248 and divide it into 414. It goes one time with 166 as a remainder. Now you take 166, divide it into 248. It goes one time, you get 82 as a remainder. And now you take 82 into 166, and you get this. It goes twice with 2 remainder. And then you take 2 goes into 82. It's 2 times 41. The remainder is 0, so that means the GCD is 2. And here is the Euclidean algorithm expressed in pseudocode. And look at how short this is. Now I know you've got some loops here, but from a programming point of view, this is very efficient, and that's why we really study the Euclidean algorithm, because encryption algorithms actually have a subroutine that is the Euclidean algorithm. And you can look at that, but that is why we study. Now the time complexity of Euclidean algorithm is actually pretty good. It is big O of the log of B, where B is the smaller of the two numbers. And that's pretty good, and that's way better than what I do. I do what I do, though, because I'm good with numbers, and I can kind of do a lot of that in my head. Okay, now an important technique, and this is also a question that I've asked on exams before, is we can express the GCDs as linear combinations of the two numbers. So here is the theorem, and this is called the Zouts theorem. I'm not really sure how I'm supposed to say that. But if A and B are positive integers, then there exist integers s and t such that the greatest common divisor of a and b is equal to s times a plus t times b. Now those are integers, so they can be negative. So let's look up here, for example. The GCD of 6 and 14 is 2. But you see that to get 2, I can say, well, 2 is equal to minus 2 times 6 plus 1 times 14. This gives you 14 minus 12. So you see these can be negative, and that's just an example of this. Now what we're doing here is this theorem is just saying there exist these integers. It does not tell us necessarily how to find them. This is really just the statement of calling those coefficients, the s and t, we call them Without coefficients of a and b. Now we don't really give a proof here, but watch what happens when we go through here and you'll see how the proof will work. Okay, so let's start with the GCD of 256 and 198 equal 18, and we could have worked through and found that that was 18, but I want you to express this as a linear combination of 252 and 198. So here's how we start. To show that this is 18, we use the Euclidean algorithm, and we go down here, we hit 0, and the last non-zero remainder was 18. But then we can say from the equation, the next to last one, we can say, well, 18 then is equal to 54 minus 1 times 36. But the previous equation says that 36 is equal to 198 minus 3 times 54. So we're going to substitute this expression in for the 36. And follow along with us doing your algebra, okay? So when we substitute in, we get this. There we substitute that, and we simplify, and we get this. Now, the first division tells us that this is true. Tells us that the first division over here tells us that 54, which is something that we have here, is equal to 252 minus 1 times 198. So if we substitute this for 54 in there, do the arithmetic, we get 18 is equal to 4 times, and this is 252 minus 5 times 198. That's the solution, and that's the process we use, and that's really, except for notation that's cumbersome, that's the way the proof works. Now we're going to use this frequently to develop several uses for results. Yes, in encryption we use this. So we want to, one of the things we're going to do in the short term is prove part of the fundamental theorem of arithmetic, which asserts that a positive integer has at most one prime factorization. Now notice that this says has at most one. So that means it doesn't have more than one, but that doesn't say it has one exactly, and that's the part of the proof that that we'll be doing later. But here, what we do is, if we write the primes in decreasing order, then the factorization is unique. So this shows if there's a factorization, then it is unique. Now we do need a couple of lemmas, again, helping theorems. You notice we're using those a lot in number theory, so that happens. Let's look at these two lemmas, and we will use these in our proof. So if a, b, and c are positive integers, such that the greatest common divisor of a and b is 1, and a divides b times c. Well, since a doesn't divide b, because the GCD is 1, then it has to divide c. And that's pretty much what we said here, but here's the proof, not in words. So suppose GCD of AB equals 1. By Vizot's theorem, there are S and T numbers that are like this. Now we can multiply both sides by C. So we take C times all of this, and I get SAC plus TBC is equal to C. But now we can use an earlier theorem to show that A must divide C, because by that previous theorem, A divides TBC, because A divides SAC, and A also divides TBC. By the second part, we conclude that A divides SAC plus TBC, because they both are equal to C. So therefore, we can conclude that A divides C. You may want to look back at the proof of that theorem, or just take the lemma as a given that we can do this. I actually like the words I said better than I like the proof. And then we're going to use the generalization of that lemma too later in the uniqueness theorem. But here's another lemma. So if P is a prime and P divides the product of A through AN, where each of those is an integer, then P has to divide one of those integers. And in fact, you could prove that by a contradiction if you wanted to. So we're proceeding with the proof of the uniqueness of the prime factorization theorem of a positive integer. And we'll use a proof by contradiction. Suppose that it can be written two ways, as a product of P1 through PS, and as a product of Q1 through QT, and those are primes such that they're increasing. Now, they may have some common primes there, so we're just going to remove those from our discussion. So if there's a common prime, we just divide it out. So we remove all the common primes, so then we have a subset of the P's is then equal to a subset of the Q's, where no prime occurs on both sides of this equation. And U and V, this is I sub U. That's a little bit of fancy notation, but that's how many of these you have, and this is how many of those you have is V. Okay, so by lemma 3, it follows that one of these P's, let's just use this one, divides one of those Q's for some K. Because no prime divides another prime, this is impossible. That's the contradiction. Therefore, there can be at most one factorization of n into primes in non-decreasing order. You might want to do a numerical example just to understand this better. Now, lemma 2 can be used to prove a result about dividing both sides of a congruence by the same number. This is a very important example. We have shown previously that we can multiply both sides of a congruence by the same integer. However, dividing both sides of a congruence by an integer does not always provide a valid congruence. And so, as an example, we know that 14 is congruent mod 6 to 8. Because if we divide 6 into here, we get it goes twice with 2 remainder. If we divide 6 into this, it goes once with 2 remainder. So those two things are congruent mod 6. But you can't divide both sides by 2, because if you did, you would have 7 and 4. But 7 is not congruent to 4. 7 is congruent to 1 mod 6, because 6 goes into 7 one time with 1 left over. And 4, if we divide 4 by 6, it goes 0 times with 4 remainder. So you see these aren't congruent mod 6. So you see you can't cancel to solve congruences in general. But there's a theorem that says sometimes we can. So we let m be a positive integer and a, b, and c also be integers. Suppose you have a, c is congruent to bc mod m, and you'd like to be able to conclude, oh, a is congruent to b mod m, but we've just seen that that's not the case. But here's what I'm saying is, if the GCD of c and m, c and m is equal to 1, then you can cancel. Let's look at the proof. Because AC equal BC, that means that m divides AC minus BC, and I can factor the C out of that, and that is A minus B. But by lemma 2, because the greatest common divisor of C and M is equal to 1, it follows that M has to divide A minus B. And that is the same thing as saying that A is congruent to B mod M. So we can cancel as long as we have this GCD relationship, that C and M are relatively prime. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all on this together. May God bless you all.